And hello, everyone. Our research is Mindful Virtual Space in Sentences, a data set of emotions through natural language classification. We will present our research in terms of introduction, methodology, experience, experiments, results, contributions, limitations, and future works. VR is a tool to measure spaces in labs instead of taking people from buildings to buildings. Also, EEGs are tools to measure feelings that are hard to tell in words. Thus, much research uses VR to measure spatial parameters combined with EEG to measure feelings. However, none of them tells the story of how people can explain their feelings or emotions in spaces using language, and how we can use these languages to explain and measure spaces or spatial emotions. Therefore, our research attempts to offer a useful natural language processing emotion classification dataset for architectural design improvement using everyday sentences. And our dataset help architects understand the virtual spatial emotions in everyday description to guide the designs. To achieve this goal, we break down the methodology into three parts: virtual reality to measure the spaces, EEG to measure the emotions such as calm or active, and sentences to build an emotion classification dataset. In the experiment, the participant can look around in the VR rooms and answer the questions in sentences. In the meantime, when the participants experience the rooms, we record their 5 brainwaves using EEG. 26 participants took part in the test. They were architectural students or faculty members from MIT or Harvard. In the end, we collect 1,402 sentences from them. For example, when we ask the participants, what is the room could become if it's a public space, they will experience the VR environments, answer our questions, and their brainwaves are recorded.
What if the room is public?
Maybe it's an office for a punished employee.
What if this room is a public space?
Like a parking garage.
Okay, this can be an office where I have rows of desks here and some storage on this side. So people walk in and you have all desks here. So it's a public office space.
Another example of our question is that what kind of furniture do you want to bring here?
Not sure about the furniture, but maybe like hanger.
The TV should not be placed like on top of the window, maybe on the side wall as a stand. Because it's cannot be hanged on the wall. Yeah, and
Prison, maybe I'll say, what do you call it? Where they put mentally violent patients.
Also, we have questions about feelings.
So I feel a little bit more relaxed and liberated. Yeah.
more relaxing, but with more. It sounds like a space for worshiping or for prayers.
Very energetic and very lively. I feel like dancing.
In a word, we have 3 tools to do our measurements. The blue one is the VR spaces to stimulate emotions and sentences. The red one is the EEG device called Muse2 to measure the emotions of calm or active. The yellow one is the audio recording, test collection, and analysis pipeline to build our dataset. We built 10 rooms with 4 parameters of shape, height, length, and width. These parameters can stimulate different feelings when the participants experience them in the VR environments. Here are the 10 rooms that the participants can see in the VR headsets. They have 90-degree views, and the participants experience them in random orders. I'm sorry about the videos. Okay, we can continue. Here are the the brainwaves from EEG can show whether they are calm or active for further analysis of emotion labeling. For example, when participant number 26 experiences neuron number 7, we record his brainwaves and sentences. We find that he has an active emotion above the 0 line, which is the baseline of his brainwave. So we label this sentence with the emotion of active. We analyze all these sentences with emotion labels of calm or active from our EEG data. For example, participants number 25 and 20 both had calm emotions in neuron number 2, 3, 7, and 10. In this way, we recorded 1,402 sentences with 2 emotion labels and translated them into text to build our binary emotion classification dataset. First, as a result, in terms of relationship between spaces and emotions, each room can arouse some participants' calm or active emotions depending on the questions and their imaginary of the spaces. Therefore, some rooms do not have distinct emotional features such as the room number 1, 6, and 5. Furthermore, the VR rooms have individual participants' differences in emotional arousal. Participants may generally have more active emotions in VR environments, such as participant number 9, 10, 15, and 26, or calmer emotions, such as participant number 7, 13, and 23. Such deviation may come from different individual spatial cognition or perception. However, you can see in the table, the minus 0.20 emotion label correlation shows significant in the relationship between height and active. This means for the higher species, most participants have calmer emotions. Second, we use BERT, natural language processing classification model, to train our dataset. We end up with an accuracy of 0.69 in 4-1 score of model. Third, we compared our dataset with other datasets like the ones from Twitter. Our dataset can give some more special emotions of calm or active other than joy and fear in Twitter datasets, and more special related information because Twitter always contains some description like food, weather, and so on. In conclusion, our spatial dataset contains 1,402 sentences and 2 labels, calm and active, to assess VR environments. Our analysis shows EEG data can measure certain spatial parameters, and we offer a useful NLP emotion classification dataset for architectural design improvement using everyday sentences. Our models can be used to evaluate machine-learned or human-generated designs in the age of AI. Also, there are some limitations of our research. First, we have only 4 parameters with some default elements, such as windows and doors, that may affect emotions. Moreover, participants in our study experience the space at a fixed point, standing or sitting without navigating the spaces in different positions. Second, we tested only 2 emotions with 4 channels of EEG, like of calm or active. Third, our dataset contains individual differences, and it's not large enough data set compared with the existing emotion classification set like the Twitter ones. For future work, first, we need to have more controlled factors such as the materials of windows and doors and sounds. In real world, the experience of space is continuous, and people experience architectural spaces not statically, but with movements. So a 3D scanning model or a moving panorama video may be another good choice. Second, more advanced EEG devices with more channels or other bio devices like GSR and eye tracking can help measure more emotion data in spaces. Third, more participants or a specific task can help us build a better data set in the future. Here are the references of our research. Thank you for listening.